Okay, this is the assignments for each chapters. Chapter 2, 3, 4, 5, 6, 7, and 9, we all have homeworks. But we didn't talk about chapter 9 because chapter 9 you did a very good job, and I think there is no problem in here. And later in the tutorial 2, we actually have some examples for chapter 9, so that's fine. And then let's see some important one. I mean, by important, I mean that difficult one in those homeworks. Some of the difficult homework question we've actually give the answer on class when we given the class, but in here to help us to review, I think it's better to talk about it again. So let's see, the first one is from chapter 2. The question in here gives us the following as the results of a sieve and hydrometer analysis. And these two analyses are all two methods help us to obtain the particle size distribution curve. We have sieve because sieve can't do very fine particles, so we have hydrometer, right? Hydrometer can got the particle size distribution for those particles, very small particles, right? Even for 0.002 millimeter, right? And so in here, this question gives us the combination of those two methods. First, ask you to draw the grain size distribution curve, and then ask you, based on the curve, determine the percentage of gravel, sand, silt, clay. According to MIT system, USDA system, and EASHTO system, so as long as you got the particle size distribution curve, then it is actually very easy to answer B, C, and D. Then let's see. First, let's see. We know these are sieve number, right? These are sieve number, but just for here, sieve number 4, because sieve number is only for sieve method. So sieve number 480170200 is for sieve analysis. It's corresponding an opening of this. And for the hydrometer method, hydrometer analysis, just copy the particle size to the opening in here. And the percent finer is given you in here. Percent finer, just copy it in here into the table. So then you know the opening, you know the percent finer, and then what's the particle size distribution curve? The particle size distribution curve is actually the relationship between these two, okay? So, let's see. If you plot, the x-axis is the opening, or we say particle size, right? And the y-axis is the accumulate of percentage, right? Then just plot those points in here, that's all. So then let's see BCD. What is MIT system, USDA system, AASHTO system? We have a table in our textbook like this. For MIT, USDA, for these three systems, actually, for gravel, sand, silt, clay, there is a particle size range. For example, for USDA system, the silt means that for silt, particle of silt means that the particle size between 0.002 to 0.05, right? And for clay, they are all the same, is smaller than 0.002. millimeter, right? But you see for gravel, sand, silt, there are some difference. So if you got the particle size distribution curve in here, if you got this, you just need to find, okay, for maybe 0.002 is in here. What's the percentage in here? This is 0.002. So 0.002 corresponding maybe around 10%. That means for clay soil, for clay is smaller than 0.002, right? So for clay it is 10%. And then you need to find the silt range for this three system and try to find how much percentage for silt, how much percentage for sand, and how much percentage for clay, for gravel, that's all. Okay? So this actually very easy. The B, C, D are the same. They just adopt a different system, right? So this question is very easy. And finally we go to this, for example, for clay. The definition for clay for this three system is the same. So the clay percentage is the same. The silt is different, but not very huge difference. Sand and gravel is the same. Because for this kind of soil, there is no particle higher than 10 millimeter. So in here actually, it is actually for this soil, it is similar. And then let's see the next one, the critical thinking problem in chapter 2. We actually give the answer of this chapter in our class. Let's see again. Three groups of students from geotechnical engineering class collected soil aggregate samples from laboratory testing from a cyclic aggregates processing plant in this place. The three samples denoted by soil A, B, C were collected from three locations of the aggregate stockpile, and sieve analysis were conducted. See this figure. So the three different students got the sample from those pile, and then do the analysis, sieve analysis, got the particle size distribution. It's like this. It asks you first to determine the coefficient of uniformity and coefficient of gradation for soil A, B, and C. That is CC and CU for soil A, B, and C. And then, based on CC and CU, ask you which one is calcium, soil A or soil C, and just find your answer. And then C is also soil obtained from same stockpile. Why they are curves so different? And then the last one is determines the percentage of gravel, sand, and fines according to unified soil classification system. So let's see the first one. Determine CU and CC is very easy. What is CC and CU? We know that uniformity coefficient is what? Is CU. It is actually the ratio between D60 and D10. CC is gradation coefficient. That is, use this equation. So in here you need to know what is D10, D30, and D60, right? So D10, D30, and D60 actually is the particle size corresponding a 10%, 30%, and 6%. The corresponding particle size of 10%, 30%, and 6% in here. So if you know the definition, actually, it is very easy to find the D10, D30, and D60 for soil A, B, and C, and then calculate CU and CC, right? Let's see one. For soil A, let's say, if you want to find D10, D10 is the particle size corresponding 10%. 10 is in here, then draw a line and a vertical line in here. It is around 0.1, 0.2, 0.3, maybe 0.4 or 0.6. So if you got the paper, it is much easier for you to got the answer, right? So it is the particle size corresponding to a 10%. And then 30, let's say in here, it is maybe around 6 or 7. In here it is 5. And then 60, it is maybe around 21. It is around 21, right? No, it's not 21. It should be 11 something, right? I give the wrong answer. But this is a way to find D10, D30, and D60. So based on this way, you can find the D10, 36 for soil A, B, and C. Then calculate Cu and Cc with these two equations for soil A, B, and C. Let's see. For soil A, Cc is 1 point almost 2, and for Cu, B, C, we always calculate Cu and Cc based on these two equations. And finally, we need to define if soil A, B, and C, which one is calcium. So we say that for a soil, if Cu and Cc satisfy these two, we say that soil is a graded soil, well-graded soil. If not, it is a poorly graded soil, like this, right? And then let's say for soil A, B, and C, if you calculated it, it is almost actually consists of this this definition here. So soil A, B, and C are all, how to say, well-graded soil. But which one is calcium? How to define calcium? We say calcium is what? Is that the soil have much more big particles, right? We say gravel is calcium, right? Then that means soil is rough, have big particles. So you see in here, big particles, of course, soil A have more big particles. Let's see if you find 1 millimeter, you can find 1 millimeter in here, right? If you, sorry, I can't find the pen. So if you find 1 millimeter in here, you will find that less than 1 millimeter to this side, soil E just creating corresponding no more than 20, and soil B is almost to 20, and soil C is higher than 20, right? That means soil A have much more particles, less than 1 millimeter. That means soil A have more big particles, right? It's much more calcium, right? That is, you see, soil A is more curved into the big particle side. So it is more calcium because it have more big particles. Then apparently, if big particles means calcium, then soil A is calcium than soil B. And let's see the third question. It is, although the soil are obtained from the same stockpile, why are the curves are so different? We say that yes. Sampling in field or the origination of soil is very difficult. Soil may be transported by water or wind, right? And then accumulated in a place. So even you got a pound of soil from the same place, maybe the soil can be different because it is set down into different place, right? So you can from the soil origination and transportation of the soil to describe this question. The final one is determining the percentage of gravel, sand, and fine according to unified soil classification system. We have unified classification system. This is for gravel, sand, and fines. Then just define soil A, B, C by gravel, sand, and fines. We said that, for example, fine for US, for the unified soil classification system, fine means that particles less than 0.075 millimeter, right? Then go to this figure to find the 0.075. 0.075 is around in here. It's around here, right? It's around here. Find this point. Find the corresponding percentage. This percentage corresponding to the fine percentage. Here, let's see, it is 0.075. My answer is maybe not very exactly, but this is a method to conduct, to do the to answer this question. I thought that this is a smaller side, this is a big side. Sorry. Actually, the final one actually is the same with the previous question. The same with the same with what we talked in here, right? Then let's see homework 3.4 in chapter 3. So it said during a compacting test in the geotechnical laboratory, the students compacted a clay soil into a cylindric mold, 4 inch in diameter and 4.58 inch in height. The compacted soil in the mold weighed 4 lb and it had a moisture content of 12%. If GS equals to 2.72, determine the following. First, dry unit weight, and then water ratio, and then degree of saturation, and finally additional water needed to achieve 100% saturation in the soil sample. The first 3 is very easy because we have this table, right? First, let's see for dry unit weight. If you want to calculate dry unit weight, you can calculate this, you can use this, or you can use the other method, right? But in here, what we use? Dry unit weight, we use actually the method I gave in here actually use this. If we want to use this water content, we know it is 12%. We know the water content. And we need to know the moisture unit weight, gamma, right? If you want to calculate the moisture unit weight, you need to know the mass of the soil and or the weight of the soil. You need to know the weight of the soil and the volume of the soil, right? Let's say the weight of the soil is 4 lb. We've already know it. And then what we need to know is the volume of the soil. The volume of soil didn't give you directly. You need to calculate it with the size of the mold. It gives you diameter. It is cylindric mold. It gives you diameter and height. Then you can calculate the volume, right? So first, to calculate the volume, and with the weight of the soil, then you can calculate what? Actually, moisture unit weight. And then with this equation, we know that water content, then you can calculate dry unit weight. So this is how to calculate this is how to calculate a cylindric mold volume. pay R, square R and H, then we can calculate. We know pay, we know H, we know R. Then we can calculate it is this. And we know mass. Or in here actually it is weight. We can transfer it into, I transfer all of this. It is in English unit, right? We transfer it into a, how to say, international unit in here, centimeters, square cubic centimeter and kilogram, right? We know the mass is 4 lb, and then we can transfer it is in kilonewton, kilogram. And we know mass, we know volume, then we can calculate density, right, in here. And we know the density, then we can use this to calculate the dry density. And we know dry density multiply the gravity gives you the dry unit weight, right? Dry unit weight. And keep in mind the relationship between weight and mass is just weight equals to the mass multiply gravity. Multiply gravity in here. So it is the same for unit weight and density. Unit weight equals to density multiply gravity. Okay? So this is actually easy. And then after we know dry unit weight and how to calculate void ratio. Let's see void ratio in here. Void ratio is in here. We know dry unit weight, right? We know dry unit weight in here. We know GS is 2.72, and then we can use this equation to calculate void ratio, right? Directly. And then degree of saturation. We know water content. We know void ratio. Then we can calculate degree of saturation with this equation. And don't worry, I will give you the table during examination. I attached the table in the final page of the examination paper. So you don't have to remember those equations. And then we know this, right? So we can use this equation to calculate ISR, degree of saturation. Then let's see the final question. Additional water needed to achieve 100 saturation in soil sample. Water need to achieve 100 saturation in the soil sample. How much water need to saturate? If we know how much water need to saturate 1 cubic meter of soil, because we know the volume of the soil is this, right? And you know 1 cubic meter, then you can calculate 942.4 cubic centimeter, right? Right? It's easy. So first you need to calculate how much water need to saturate 1 cubic meter of soil.咋了？
张老师，我们能换一个房间吗？这个我们布置一下会场，您能不能去
啥时候
306
明天
那个课？
就是您几点钟用到这里？
我在给学生录网课。
哦，现在是吗？
那大概什么时候结束？
要不半个小时后？
可以的。
可以，306。没事，他在这里。
不是，
这他已经
因为我们这个课本来是在这儿上的，然后系统登的我的所有的课件什么之类都在这个上面。
行，好的，那练好了跟我们说一下。
好的，行。
好的。
So you need to calculate how much water need to saturate 1 square meter of soil, right? Let's see. We know what? We know the saturated mass. Saturated for 1 for one cubic meter of soil, the saturated mass minus the moisture mass, that is the water you need to saturate it, right? That is how much water you need to add to the moisture soil to get it saturated, right? So, what's this? Now, the volume is what? The volume is 1, right? So actually, this equation equals to this, right? Because saturated mass, moisture mass, and water mass equals to density multiplied volume. Density multiplied volume, but we use different density in here. So, if we know this, and volume now is 1, and then, because volume equals to 1, the difference between the saturated density and the moisture density actually gives you the mass of water you need to add to saturated 1 cubic meter of soil, right? Understand this? From here to here, that is because mass equals to density multiplied volume, right? And from here to here, that is because volume now is 1 cubic meter. And then actually the MW we need to saturate the 1 cubic meter of soil is actually the difference between saturated density and moisture density. So, what is saturated density? What is saturated moisture density? Let's see in here, because saturated density can be calculated with saturated unit weight, right? If you use saturated unit weight divided gravity, then you got saturated density, right? And for moisture density equals to what? We have actually an equation on our textbook. So it is this. So the moisture density equals to this. This is the equation. And again, for saturated density, it equals to this. You see, it is actually very similar with this. So these two equations, with these two equations, actually, we can go to row set and row. And the difference between these two is the water need to saturate 1 cubic meter of soil. You know 1 cubic meter of soil, how much of 942.4 square centimeters, and you can calculate it, right? First, translate it to how much square meter, then you can calculate it, right? This is the method to answer this question.